This video is for topic 4.8, Introduction to Acids and Bases. The objective for this topic is to identify species as Bronsted-Lowry acids, bases, and/or conjugate acid-base pairs based on proton transfer involving those species. So when we think about acids and bases, we're going to think about two models, and then we're going to focus on the Bronsted-Lowry model. As a note, we're going to spend an entire unit later on focusing specifically just on acids and bases and how they react. This topic is just an overview. So how would we identify the components and just identify that a reaction is acid-base? So there's two different models of acids and bases that we're going to follow in this class. There is another one that if you take organic chemistry, that you will look at in organic chemistry as well. But for our purposes, we're going to focus on the Bronsted-Lowry definition and the Arrhenius definition. According to Bronsted-Lowry, acids are proton donors. So anything that's an acid is going to give up or lose a proton or a hydrogen ion. Bases are going to accept protons or hydrogen ions. That means bases are going to gain protons. So usually we think about gaining and losing electrons. In this case, we're thinking about gaining and losing protons or hydrogens. So we call hydrogens a proton because hydrogen plus one is literally just a proton. So normal hydrogen, hydrogen one, is a proton and an electron. If it has a plus one charge, it's lost that electron. So it's literally just a proton. So you'll see those two used interchangeably, proton and H+. The Arrhenius definition of acids and bases is probably one you're familiar with from previous classes, where acids donate the hydrogen and bases donate the hydroxide or the OH. And so in both of these cases, the original compound is losing something. It's either losing a hydrogen if it's an acid, or it's losing an OH if it's a base. We're going to focus primarily on the Bronsted-Lowry definition of acids and bases. So really what we're looking at is just the transfer of protons. So acids are going to give up protons, bases are going to accept protons. Before we move on, we need to talk a little bit about water because it's very unique. So water has both a proton and a hydroxide ion. So it's made up of both an H+ and an OH-. And it's in equilibrium. So you might notice that this reaction has an unusual looking arrow. So it has two sides. This means that water is in a constant state of breaking apart into its ions and forming back into water. What this means is that water can sometimes act as an acid by donating the hydrogen, and in other times it can act as a base. So it can either donate the hydroxide or the hydroxide can accept a proton to form water. We call this amphoteric, if something can act as both an acid or a base. In pure water, some of the water is always going to be ionized to produce the H+ and the OH-. In a neutral solution, so something that has a pH of 7, the amount of hydrogen is equal to the amount of oxygen, or the concentration of hydrogen is equal to the concentration of hydroxide in the solution, so that they cancel each other out, and it maintains neutrality. The last piece with Bronsted-Lowry acids and bases are their conjugates. So when acids lose or donate a proton, they form a conjugate base. When bases gain a proton, they form conjugate acids. So you should be able to go back and forth between an acid and its conjugate base or a base and its conjugate acid. So if we look at our two examples, in this reaction, we have NH3 or ammonia reacting with water, and it forms ammonium ion and hydroxide. So when I go to think about this, if I were labeling this as my acid-base, conjugate acid, or conjugate base, my acid and base are always going to be in my reactants. So I'm not going to have any conjugates to start with. Your conjugates are always in your products. Your acids and bases are always in your reactants. So I'm going to start with NH3 because that's my first one. Why not? And I'm going to go find its partner. So it's a reactant. So I'm going to go find its partner product. So it's either going to be NH4+ or OH-. Well, we're only talking about gaining and losing hydrogens. So the only product that is either more or less hydrogen is NH4+, because I can't gain or lose my nitrogen. That has to stay. So when I go from NH3 to NH4+, I'm gaining a hydrogen, which means my NH3 is a base because bases gain hydrogens, and that makes my NH4+ its conjugate acid. If I think about this the other way, my NH4+, in order to become NH3, has to lose a hydrogen. Acids lose hydrogens, therefore my conjugate acid becomes my base. That leaves my water as my other pair. So that leaves water as my acid and my hydroxide as my conjugate base. And I can verify this by comparing them. So H2O compared to OH, H2O loses a proton, loses an H to become OH minus or hydroxide. Acids lose protons, which means H2O is an acid, which leaves OH minus or hydroxide as my conjugate base. If I go back the other direction, my conjugate base, my OH minus, gains a proton, which is what bases do, to become H2O, which is my acid. Strength of acids and bases has to do not with pH, but with how much they dissociate. So this is a very common misconception, is that strong acids are going to have a certain pH. And that doesn't have anything to do with pH. pH has everything to do with the concentration of the hydrogen ion, which is what we're going to talk about later when we talk about acids and bases in more depth. When we talk about strong and weak, we're talking about dissociation. So how much they break apart into their ions. Strong acids and bases are going to completely dissociate into their ion pieces. So if we talk about an acid, a strong acid is going to completely break apart into its proton and then its negative ion piece. So there's not going to be any of the acid together as a whole molecule. It's always going to be completely split up. A weak acid means that it doesn't do that. A weak acid means that some of it will ionize, some of it will break up, but some of it will stay together. And again, strength is not at all related to pH. So just with pH, something that has a very low pH is acidic, something that has a high pH is basic, something that's 7, a pH of 7 is neutral. Has nothing to do with strength, nothing to do with this dissociation, has everything to do with concentration. And that's something that we are going to look at later.